Hi everyone. So the other day we learned how to solve a system by graphing. That meant finding the intersection point of two lines on a graph. Today we're going to do the same thing. We're going to find where these two lines intersect. If you look at example 1, they're both the equation of a line. We're going to find the intersection point algebraically through a method called substitution. When you're using substitution, you want to first look for a variable that's isolated, that's by itself. So either y equals something, I'm going to put a box to represent that something, or x equals something. It could be either variable isolated. So I notice in the first equation I have y equals negative 4x minus 3, so I can box that out, and I can then substitute that expression in the place of y in the second equation. So that what I'm doing is I'm going to now write negative 4x minus 3 instead of the y, and then minus x equals 7. I'm doing that so that I can now create an equation that only has one variable, so that I could actually solve and get a numerical value for that variable. So I'm going to solve this equation. I'm going to combine like terms. I have negative 5x minus 3 equals 7. I add 3, negative 5x equals 10. I divide by negative 5, x equals negative 2. Once I get my x value, I can plug in that x value into either of the two equations. They'll both produce the same answer for y. Okay, I'm going to go into the first one because it's usually easier to go into the one where all the numbers will be on one side of the equation. So it'd be negative 4 times negative 2 minus 3, so that's 8 minus 3, the y value is 5. So my x value is negative 2, my y value is 5. That means that the point of intersection of these two lines is at negative 2 comma 5. Okay, continuing to example 2, you'll notice that on purpose I did it so that this time in the second equation the x is isolated. Let me fix that. So just to kind of point out that it doesn't always have to be y equals, it could be an x equals. So I have x equals 3y. So that means I'm going to plug into the first equation. You're always going to go into the opposite equation. I'm going to substitute 3y in the place of x. So instead of 5 times x, I have 5 times 3y minus y equals 28. And I'm going to solve because now I'm just with one variable. So I have 15y minus y equals 28. That's 14y equals 28. Divide y equals 2. And then I take that y value and I plug it into either equation, doesn't matter which one. I'm going to go into the second one because it's easier. X equals 3 times 2, so x equals 6. So my x value is 6, my y value is 2. That means that my point of intersection is at 6 comma 2. Okay, in our third example, I have both equations with a variable isolated. I have y equals 2x minus 3, and I have y equals 8x plus 3. So basically you can pick either one to substitute. You're basically going to set them equal to each other. So 2x minus 3 is equal to 8x plus 3. And you solve from there. So I will subtract 2x from both sides. I will also subtract 3 from both sides. I have negative 6 equals 6x. When I divide by 6, x equals negative 1. I'm going to take that value, plug it into either equation, doesn't matter. I'm going to go into the first one. 2 times negative 1 minus 3 is going to be negative 2 minus 3, which is negative 5. So my point of intersection of the two lines is negative 1, negative 5. Okay, continuing now to example 4, where I don't have a variable that's isolated. So what you have to do is you have to isolate a variable. But in order to do that, you have to be strategic. You do not want to isolate this y or this x because both of those coefficients, the 8 and the 6, tell me that I'm going to end up with a fractional answer. So I want to avoid fractions. So if you look carefully, the only variable that would be really easy to isolate that would avoid the fractions would be the first x here because it has a coefficient of 1. You want the coefficient to equal 1 on the variable that you're isolating. So I will add 3y to both sides. That will give me the equation x equals 3y plus 5. Now I take that expression and I sub that in for x in the second equation. And so whenever you're substituting an expression, it would be the quickest way, the most efficient way would be to substitute an expression that does not contain fractions, okay? So 6y plus 8 times, now I'm subbing in 3y plus 5 equals 10, and I'm going to solve from here. So 6y plus 24y plus 40 equals 10. I have 30y, and I'm subtracting the 40 onto the other side, equals negative 30, so y equals negative 1. I'm going to take negative 1 and I'm going to substitute it into either equation. It doesn't matter. I'm going to go into this one that I created, right? It's the alternate version of the first equation because it's going to be easier because all the numbers will be on the right side. X equals 3 times negative 1 plus 5, so x equals 2. So my point of intersection of the two lines is 2, negative 1. It would be really great right now if you could pause the video and see if you could try example 5 and then replay it and check to see if your strategy was correct. Okay, the solution to example 5 is that when I look for a coefficient of 1, the second equation with the y, that y has a coefficient of 1. So I'm going to isolate y. Y equals, I'm adding 6x to both sides, so 6x minus 7. I'm taking this expression and I'm subbing it in the place of y in the first equation. So I have 3 times 6x minus 7 plus 2x equals 79. And I'm going to solve from there. 18x minus 21 plus 2x equals 79. Combining the x's and I'm adding 21, so 20x equals 100 and x equals 5. I'm going to plug that in to my version of the second equation. Y equals 6 times 5 minus 7. That's going to be 30 minus 7, which is 23. So my point of intersection is at 5, 23. All right, you should be able now to complete tonight's homework on substitution. All right, thank you.